So I don't know if he was trying to avoid the whole syntax semantics discussion in order to just get straight to implied naturality via the types of the programs.
Mm.
So, I mean, because what I found really confusing about this is that we don't really have a semantics. Like, I mean, we do clearly, but it's not like we have terms and formulas separated uh, explicitly all the way throughout the paper. But I think it would be easier to understand if we did have that.
It's sort of like I when I read what he's saying at the bottom of the of page 4. Just an alternative is to read a type as a relation. If a and a prime are sets, we write curly a colon a uh, two-way arrow a prime to indicate that a is a relation between a and a prime. So like I kind of read that as like using the same notation for the uh, for the syntax and the semantics, like saying, okay, you could write this down with just symbols and just have it be a pure syntactic thing, but like there's a reason why the syntax and semantics like sort of looks similar is because when we use the syntax to talk about the semantic things, and so it's kind of I'm just reading it as like an overloading of notation to say like okay, we could think of like the curly uh, a arrow a prime as like that's a term on the left and a type on the right or something. Um,
So are you thinking of curly A as the term, and then A if and only if A prime is the type?
um, I guess it would really be uh, is what you're saying is that the situation is more like you have lowercase a is of type a prime is of type curly a, and like the semantics of curly a is that it's a subset of that.
So the point that I'm making is where the overloading of notation actually occurs is to the right of the colon, right? So saying A if and only if A prime, we're looking at A and A prime as sets there.
Hmm.
But but we use capital Roman letters for types.
Okay.
So so it's as though where we have two layers of semantics here. It's as though we have types, which are some letters inside some formal language, and then we interpret. It would be helpful if I wrote this down. So yeah,
Okay.
let me just
Yeah.
load up my iPad.
It wasn't immediately obvious to me that when you said types that it was going to be like a purely syntactic thing because like types are also spoken about as like semantic objects, just like sets are semantic objects.
Uh, but how? So yeah, this is the part of the discussion that I want to make precise. So I don't think you can. Now, when you say sets are used as semantic objects, I mean, what? Oh, hey, my drone thing worked. So when I loaded up my iPad, it just went straight onto my Fleetwood character.
Yeah, cool.
Um, okay, so here are the types, right? The types are just these letters, A, B, C, dot, dot, dot. And we have type constructors as well. So it looks like we have product and is the arrow thing actually a type? No, I don't think it is. So, oh, we do have arrow, but it's not that arrow. So we've got this arrow constructor,
Mm-hmm.
and then we have for all as well. I don't know what to. Yeah, I guess it's something like this. And here we've got variable, so atomic types as well, right?
So wait, what's is A B C different to X Y?
Yeah, I guess so. So
I thought they were all just
th
type variables.
yeah, so if you want to do it more, it's just my laziness of notation. Okay, so types. Got variables. So we start off with a just a countably infinite set of variables, and then if A and B are types, next is a variable, then A cross B is a type, A arrow B is a type, and for all X, well, I guess I can just say A. Yeah. So A might have a dependency on X, but you don't really need to write that. In fact, I've always found it kind of confusing to write it, but
Hmm.
maybe some people like it. I don't know. Let me just make sure that's everything that's happening in this system, because is there a relation? Is there like a subset or something?
Um,
No, no. He's got this paragraph here. So right above the paragraph before the one that you mentioned on page 4, um, we have if A and B are types, then A cross B corresponds to, yeah. So A cross B is a type, and then A arrow B is a type,
oh, there's A
and then
star.
for all X, oh yeah, you're right, and A star, A star. Okay, so that's the type system, right? And I think that this is pretty weird because what on earth is a type system without formulas or terms of any form, right? I mean, normally you introduce types of terms. I mean,
Hmm.
listen to the name type, right? It's like I have types, but not things. So I don't have my things to be of different types. I just have the types themselves.
Hmm.
That's kind of weird, right? And
Actually, I think
that's where
I've heard a
yeah,
lot
you go.
of I've heard like some Haskell blog post about like someone doing like a programming interview and they like build uh like the natural numbers, the type of natural numbers or something in Haskell, and then they never like they just use like types the whole time and never actually have like terms of
Mm,
a type. They just sort of do constructions on types, and
yeah,
the interviewer like says something like exactly what you said about like types are supposed to have things that are of them, like
of them,
elements of
yeah,
the type. Like
exactly,
you
right.
can't just be working with the types and then the interviewee's like, no, that doesn't sound right, and just like goes
What?
back to it.
Okay, so you could, right? I mean,
Isn't that how it like works in like there's objects in a category and you don't necessarily have like elements in the objects, like only in certain situations.
yeah, but I wouldn't say that's a totally legitimate analogy. So look, the thing is, a type system without terms just descends to some syntactic system, right? I mean, if I talk about the untyped lambda calculus, then how do I know that this is not a type, right? I mean, we call that a term, but this term is not of any type because it's the untyped lambda calculus, right? So who are you to tell me what this thing is? It's a term, but it also just might be types. I mean, in System F, you do get types that look kind of similar to it, right?
Mm.
And this is literally just a syntactic system with a rewrite rule.
Yeah.
So, like what is a type at a certain point? So I think that you can do meaningful things with systems that only consist of types. However, you probably need a rewrite rule in order to do anything interesting with it. And secondly, that's not what Wadlow is trying to do. Wadlow is trying to prove stuff about programs of these types purely based on the type itself. So Wadler's whole point is that what was it? For all x arrow x or something? Yeah, x star. Okay, so if you're a program of this type, then you know something about that program. You get the theorems for free. I mean, look at this sentence, right? He said R is of type for all x dot x star arrow x star.
Yeah.
And what we end up concluding is A star O R A because R A R prime composed with A star.
Mm-hmm.
So you get this naturality thing. And this is clearly the point of interest here is R. This is the program in some way. And if we're talking about types and we're talking about programs, then the programs are going to be the terms in that type system.
Mm-hmm.
So there are terms floating around inside this paper,
Yeah.
but he doesn't articulate that distinction.
5.2 is titled terms. Associated with each
Oh, is
type
it?
A in U is a
Okay.
set dA of the values of that type.
I see. So maybe it does talk about it. Is he just saying the elements inside the sets? Because that's consistent with what he is doing this entire time. I mean, here he takes that. So let's have a look. Associated with each type A in U is a set dA of the values of that type. Mm-hmm. Mm-hmm. Oh, cool. Okay, so yeah, I didn't get up to this part of the. Ah, interesting. So yeah, maybe he does do the whole semantics thing more rigorously, but earlier in the paper, he's trying to make the important point without going into this level of precision.
Yeah.
So, so this is helpful. Okay, he says he defines the semantics. So shall we just read this and see if we can just understand the semantics?
Yeah, okay, where are we starting from?
Let's start at the top of 5. So semantics of polymorphic lambda calculus.
Uh-huh.
We've we will give a semantics using the version of the frame semantics, which I've got no idea what that is. We first discuss the semantics of types and then discuss the semantics of terms. Oh, this is going to answer our question, I reckon. Okay, types. Universe U of type values into operations that construct types from other types. That's already a little weird. Is he talking about the same system? So this must be. So the polymorphic lambda calculus doesn't have products. Okay, that's reasonable. So let's understand um, our syntax. We have terms
So wait,
are either.
is there any content in U being a universe? Like what is there some background to what that means?
I don't know. So
Okay, well, no, 4 is pretty short and just goes through what the polymorphic lambda calculus is. So maybe
yeah,
we start from there.
yeah, I was just going to write that summary. So
Yeah.
they're the types. These are the terms. And then lambda capital X dot T. Yeah, that makes sense. TU. Okay. So that's system F, right? let me have a quick look on Wikipedia and see if it just has the same presentation. Yeah. Wikipedia just says system F, also known as the polymorphic lambda calculus or second order lambda calculus. Yeah, this makes sense. So one thing to notice is there's no product, which is good.
Why is that?
Lambda calculus doesn't have product.
Oh, okay.
I mean, product in the lambda calculus was introduced, I believe, in that Curry-Howard-Lambeck correspondence, if you've heard of it, that the category of Cartesian closed categories is equivalent to the category of lambda calculi. That only holds if you put products into the type system of the simply typed lambda calculus. And
if you have like a
so that's
element type and you have like the type like if that's the type bool, then like bool to x is the type of pairs in X, right?
Yeah.
I guess you want like then you can only have pairs of the same type. That's not pairs of like one from one type or one from another.
No, you can. So it's just very similar to this rule, right? So if you give me two types, I can form their product. You cross feed.
I mean, without the product, can you reconstruct the product using the function type and like some two element type? But I don't think so.
Yeah, I think you can, right? So I wonder if it's something like this. Because
I think, did you write that wrong? Did you mean to write the brackets in the other way? As in,
I don't know. Let's have a look. No, I was trying to do this. So you've got inside set an isomorphism between these two. Oh, wait. Maybe that is what you've said. Yeah, so B to C to A. Yeah, possibly. Yeah, so I think that there are ways to mock product using arrow because of this, right? So
but it's like functions out of the product you can.
Yeah.
But not like.
Yeah, but the product itself. So I don't know how you can get this. I don't know how you would define that object just using hom sets. I don't know if that's possible. Unless you have a terminal object. Because then you could say so hom 1 into, yeah, like in generator, like what we were talking about last time. However, the order's the wrong way. So that's isomorphic to A cross B, right? And I was hoping that I could use the exponential adjunction, so this guy here, some way, to rewrite this only in terms of the power object, because keep in mind, this is hom A to C. which is going to be the semantics of A arrow C.
Yeah.
So if there was a way to rewrite this, but I don't know, I don't see it, because you need A cross B on the left. Anyway, I think that's kind of a distraction. So there's no product inside the system. Also, another thing to note is that there's no application in the types, right? So
Isn't that the second beta rule?
the second beta rule is not, yeah, there is a second beta rule, but there's no application. Like, think about this rule. There's no analog to that inside the types. So you can't build the application of two types. But if I have lambda,
only
yeah,
if the first thing is like an abstraction can you apply.
so the apply is kind of hybrid. So you've got this rule, which is the application of two terms. That's familiar from simply types lambda calculus. But then you've got this. This is the application of a term to a type, right? That is not the application of two types. You see my point? So
Right.
coming back over here.
Did you add TU there? What is that?
No, that was. Oh, wait, that's T. What does he mean by T sub U?
Wait, yeah. So, sorry, I thought you were saying that there's no application of. Wait, is that like T is a term which is like defined polymorphically, and it has like free type variables in it, but you can specialize it to U by like writing a subscript U.
Yeah. Do you want an example?
Yeah.
So. So you can form. So we have a variable x, and that's supposed to be of a particular type. Let's call that x of type x. Does that make sense? So it's a variable. It's a term variable, lowercase x, and it's of type variable, capital X.
Yeah.
And then I can perform abstraction on the level of terms, and I get lambda x dot x, and this is of type capital X arrow capital X. And then
okay. Yeah.
So this is the rule var that I've used, and this is the rule abs that I've used. And then let's say v abs for variable abstraction, because I can then do that to get lambda capital X dot lambda x dot x, and that's of type for all x dot x arrow x, right?
Yeah.
And then I can use this one. Let's say v abs was a little bit of a weird thing to write. Maybe that should have been t abs for type. Okay, and then we do t app. Yeah. So T app, and let me just put some type variable y there. So that's this little type variable. Okay, and then I get lambda x dot lambda x dot x apply to y,
Mm-hmm.
and the second beta reduction rule is does this even reduce? Yeah, it has to. So how do I even write the type of that?
So wait,
So
what you did there? Shouldn't you have written? It's like the second beta reduction. It's sort of like a subscript u. It's like to make it distinguish from looking like it's a term or something.
yeah, so that's what Wadler's done in this paper, but I haven't seen that before.
Uh
So
huh.
normally you just write it right next to it.
Yeah.
It
Okay.
I think it doesn't really matter. But here's a point that I want to make. Like, what is the type of this term, right? You might be tempted to write it's of type for all x dot x arrow x applied to y, right? But that's incorrect. That is not even a valid type
Mm.
because the type system does not have application, right? So
It just sort of has like the before and after of the application, and you
exactly, yeah. So that's incorrect. But what it
there's not
is
really
of
a
type
before.
y arrows y,
Uh huh.
y arrow y.
Yeah.
Okay, and then this should reduce as well. So I guess it has to be this, but I can't find the reduction rule.
Wait, why are you writing it like this and not just like another line, like another
Because
divided
this
line?
is a reduction as opposed to the building of a term.
Oh
So
right. Okay.
yeah, you've got I've used this in order to build up a term, and then that term reduces to another term, which is this one, which has its own uh, tree construction, right? So variable x of type y abs
Right. So
lambda x.
because the beta and eta conversion rules, and there's like an equivalence relation you derive from those. So in terms of the context of this deduction tree, like the thing that we reduce to is like is thought of as equivalent to like what we wrote at the bottom of the tree.
I think so. So you're just saying, I mean, this has redundancy in it, is the point. You can see that this appears as a subtree of it, but that's not actually the most important point. The most important point is that you have terms, but you have more than terms. You have terms and reductions of terms, right?
Mm.
So each individual term has its own tree that constructs that term. And so you get a mapping between full construction trees of terms to other full construction trees of terms, if you want to think about it like that. But I don't think that's the easiest way to think about it. I'll just think about it as you have valid terms that are brought about in some way,
Uh,
and you have reduction rules that relate those terms to other terms.
okay. What happened here below? Like so, I follow here to I follow the first reduction, this
Mm-hmm.
thing, and then what did you do after that? That
Oh, I
became
was just making the point that this thing itself has got its own tree, it's got its own constructed
oh right.
construction tree. I don't know what to call it.
I thought this term was above this line, but it's
No,
no.
no.
Okay. Yeah. Okay.
I don't know how to make that
So
clear.
I guess you were saying that,
Okay.
yeah, so there's no application rule on the types. Like, it's,
Yes.
I guess that's kind of just avoiding the need to have an equivalence relation on types, and then every term has a unique type, and there's not like
Yeah, well, this is the thing. Like, I don't know the answer to that question, but I think that it's significant that you don't have application in the typing system because you don't have rewriting in the typing system. You have substitution, but you don't have rewriting. So it's not like you have a, oh, did I say term? I was meant to say type. It's not like you have a rule that reduces a type to another type.
yeah.
There's just none of that. So you don't have rewrites inside the typing system. Whereas if you were to have rewrites in the typing system, then you would have computation inside the typing system,
Mm.
right? And it's easy to think of a way that you could set that up. You could just literally make the typing system um, the untyped lambda calculus. Do you see what I've done there? So you just replace
Uh-huh.
that with application, and now you have the untyped lambda calculus. I mean, it's not exactly the same because you need to put variables in here as well.
Yeah.
Anyway, whatever. Just imagine a new system where the typing rule is the untyped lambda calculus, but then you also have rewrite rules inside the terms. Then all of a sudden you've
So, he disappeared again. Hello.
hey, right. Sorry about that.
Okay.
Got too invested in the math. Okay, so going back to the paper, yeah, we do have the beta and eta conversion rules. So that's kind of important. So let me just write that on the same board.
Mm-hmm.
Working on. Oh, so he has eta reduction as well. I think I don't care about that. I'm just going to write down beta. So lambda x of type u dot t applied to u. So t and u are terms. That reduces to t u over x.
I think you
And
need to
then
say, wait, which rule is this? This is the, oh, this is the first one.
it's just beta reduction. Yeah. Okay. And that's reflected here.
Mm-hmm.
Okay. Semantics of polymorphic lambda calculus. So now we give a semantics for this. So we start with the universe U of type values. I wonder if that is significant. That's the kind of sentence that I normally just ignore on first reading and then
Mm.
wait until I find the point where I get stuck and I think to myself, oh, maybe that's what they needed the universe for. Okay, and two operators that construct types from other types. He's already conflating type. Yeah, does he mean type values? Construct type values from other type values? Who knows?
What's a
There
type
is a
value?
distinguish. Well, he says you've got. I think the type value would be an element of the universe U, because he says we're constructing the model. So we start with some universe of type values, and then we define two operations that construct types from other types. But we already have those constructions. They're part of the syntax of the polymorphic lambda calculus. So I think he's talking about type constructions. Sorry, type type value constructors is what they're meant to be, because you want to interpret.
Wait, are the
So
type
on the
values
semantic,
the elements of the types or the types themselves?
the no, I think it's the elements of the universe.
Right, but wait,
Makes sense.
are you what do terms get interpreted as, and what do types get interpreted as, like type values? Sorry, the type variables in the syntax. What do they get
The
interpreted?
type variables, I think, get interpreted as elements of this universe U that you've started off
So
with.
type values.
Yeah.
Okay, and the terms of the types are like not, they don't appear here, or they're not, they're just there.
Yeah, that's the next section. So you see how this is saying types, and the next section's terms. So associated with
Right.
each type is a set of values for that. Oh, weird. Oh, that kind of makes sense. And then, yeah, then he's going to do something with the terms in a minute. Okay. So I don't understand the next sentence. Who cares? Let T be a type with three variables x bar. So T be a type with three variables x1 down to xn. Okay. So the A bar is a type environment for x bar if it maps each type variable x bar into a type value u. Okay, so then we need a function. And this can be chosen arbitrarily. And he's calling that A bar, but I think that's bad notation. I'm going to use phi. And this goes from the underlying set of their sequence, so x1 up to xn, into the universe that were fixed right from the start. So fix, and you can just be a set, fix a set u. Done. Okay? So first we make a decision for the interpretation of all of the variables. That seems to be what this is saying. Yeah, but I, again, wouldn't use this notation. So alternate
So like you don't,
notation.
you said that like you just choose one phi and that's what you're gonna fix for your whole semantics, but is it like that, or can you have like, can you talk about many different
Yeah,
phis?
yeah, it is for the entire semantics. So you'll get different things if you interpret the variables differently, but that's standard, right?
Yeah.
The variables can be anything, and then the interesting part is how the constructors get interpreted so that you can build new stuff out of those initial building blocks, right? So I was just thinking about it like this. I think that's the easiest way to see it. Like all we're doing is picking an element in U for each xi, right? And you can notate that as this double brackets thing, the interpretation of xi.
But
Okay.
it's not just for uh, but he's not. But here you've used the double brackets only for type variables, but the part just below it is like how to extend this to like any uh to all of the types, not just the type
Mm-hmm.
variables.
Yeah. So this one's in choice, and then he defines how to extend this to the rest of the types.
Uh-huh. I guess the A bar is like part of the brackets in your is sort of implicit in your
Yeah.
notation.
Hmm.
Alright. Yeah.
Because, I mean, what does, okay, so what's he saying here? What? You see, I think this notation is so confusing. Like his first sentence, double bracket X, A bar equals A bar, double bracket X,
Mm.
is saying this. Is saying the way that you interpret the variables inside the context, which is this,
Mm.
is via that function, A
Mm.
bar.
Yeah.
So he's literally just saying xi double brackets is are these elements in U. It's kind of a redundant statement and it makes it confusing. It's the same for the rest of it. So T arrow U is defined to be equal to um, T arrow U, and then the question is, what is that? What is this arrow? What is this? And I think that he mentions that earlier as well, which I didn't understand. Yeah, there is a distinguished set of functions from U to U.
No, he's not talking about that at all.
So,
That's just the first arrow. The into operations arrow and for all A that construct types from other types. So
mm,
brackets T A bar is a type and brackets U A bar is a type, and so therefore you can uh like or maybe I should say type value. Um and so you can put an arrow between those two type values and you get another type value in U.
yeah, so he does mean type values earlier, right? So the point is, right at the very start, you fix a set U, you fix an interpretation
Mm-hmm.
of arrow and for all, and then we're going to use that.
Yeah.
But are there constraints on what those interpretations should be? I feel like
Maybe
there
he's
has to
just
be.
setting the scene for like this is the space of semantics that you can put on it, like not a specific semantics.
Uh,
Like
mm,
you could choose to like choosing to interpret type variables as a plain set or a relation on two sets.
yeah, but you would want this semantics to respect the reduction rules. So these can't be anything. Like there's
Yeah,
concrete restrictions on it.
yeah.
This is weird. I think it's probably implied by the rest of the paper. So if you go back to the example section, which I wrote the tutorial based off, then you see how he's like saying the product, for example, is the set of pairs, and then arrow is the set. Yeah, you see, I think that he means that this arrow actually means the set of functions from this set to this set.
But wait, wouldn't he have written that? Because it's also not that if it's the relation story, right?
But I kind of got that from the relation story. I mean, the relation story is saying that a arrow um where does he say it? So any function a from a arrow a prime may also be read as a relation. So that seems to be a particular function. But how do you pick which function it is? So that's
I think you mentioned that to define the the relation curly A arrow curly B.
yeah. Hmm. So what do you normally do with arrow? You normally say um wait, I'm gonna move my character again. Let me have a look at my topos theory notes.
Maybe we should play a
So
sound when you're about to be like kicked.
that's a good idea. Yeah.
Something pleasant but also noticeable, I guess.
Yeah. So going to the interpretation. Oh yeah. Yeah, the story's different in topos theory. It doesn't make sense. In topos theory, you have a label for such things, and these labels come from the topos that you're working in. So for every morphism, you introduce this label F of arrow type, and then the interpretation of such a thing is just going to be that morphism that's got the same name, right? So since this comes equipped with a reference to a specific morphism, you can use that morphism in the interpretation. But we don't have that here. We just have T and U, which are both completely random sets, right? Because based off what I've said, you could have the context consisting of a single variable x, and then you take a u to be some completely random universe. Maybe that's the universe of all sets, right?
Mm.
Then what I've said is that this is just a completely random set, right? That's an element of u somewhere. And so then the question is, how on earth do I interpret that x arrow x? So what I've said is that this is x arrow x. So if that's just a function, then which one? How on earth would I pick that, right?
Wait,
So then
isn't
the other
that
option is to, yeah,
wait, what? I thought you were gonna say like the set of functions.
yeah. So you could define that as the set of functions. Maybe use notation like that or something, and that's what I think it is. But I don't think that he has explicitly said that here. But I think that he's implicitly saying that it has to be that it's defined to be the set of functions from TDU.
I think the fact that he said universe of type values and just that arrow and for all construct types from other types is that I think explicitly there's supposed to be flexibility there. But I do agree that like
Mm,
surely it should obey some kind of sensibility. Um,
yeah,
I
I'm
guess
not so
like
sure. I mean,
it should just obey like whatever coherence you need uh, with the like typing rules, and the well, maybe not the typing
mm,
rules, like the beta and eta
the
reduction.
reductions, I
Yeah, the
think.
reductions.
Yeah, I mean, you've got soundness, right? So if you see this proposition just before section 6, for all x full x bar t and t. If x bar x entails t, then x bar proves t. Yeah, so that's some kind of coherence across the syntax to the semantics,
Mm.
and then he doesn't prove that. So you can't work out what he means.
So
Um,
yeah, I mean, it probably is just a rule that like whatever the operations arrow and for all are, they just need to respect the
yeah,
reduction rules.
yeah. Okay, and then we also have the parameter. I can't say that parametricity theorem, which is, I think, the most important part of the paper. So there's another theorem here that needs to be respected as well. Yeah. So can you see this proposition that's labeled parametricity? It's at the bottom of page 11 on the left column.
Mm-hmm.
And then it's got parametricity, and you can see the first line of the proof. The proof is a straightforward induction over the structure of type inferences.
Mm-hmm.
So he's clearly using some relationship between the cohesiveness of the constructors in the syntax to the constructors in the semantics,
Mm-hmm.
but it doesn't look like he details it there. Yeah, this was kind of my impression when I was reading this paper. So there's a lot of um, kind of messy stuff swept under the rug, which I think is important. I think it would be an awesome exercise to kind of do this paper a bit more precisely and prove these results with a proper semantics and well-defined interpretation of the terms as well as the types and a proper proof of the soundness theorem. But that's a fair bit of work, but that would be like a valuable thing for someone to do, I think.
How well, like how in depth have you read this paper? Um, like otherwise,
Not very in depth.
say like although it's like not clear that he's like completely stated everything correctly on like our reading of it, like that might still
Yeah,
be true, but we just haven't properly read the whole thing.
you haven't read it properly. Yeah, for sure. I mean, modulo that. The only real technicality with which I read it was when I was writing up that tutorial exercise. But I wanted to understand it because it seemed like it achieved what the semantics community are always claiming that their field of math will eventually achieve, which is we can abstract and study um, properties of programming languages by constructing a mathematical theory of types that kind
Mm-hmm.
of sits above it. So what you would want that to look like is exactly what Wadler's saying. So if I know that this program is of this type and you tell me absolutely nothing else about the program, so in particular, you don't tell me how you've implemented it, you don't tell me what machine you're running it on, you don't tell me um, about what programming language it's written in, etc.,
Mm.
then I'm able to tell you this fact about the program,
Yeah.
right? So that's what the whole semantics community are trying to do, and this seems like a really good concrete example of it.
Mm.
But like yeah, I couldn't
Because
extract immediately all of the technical details to
the
make it work.
reason why that works is because like although it can be like any program in any programming language, like it's sort of it's the fact that it has to work polymorphically is the real constraint on the program that like
Yeah,
prevents it
but
from being able to
it's
work.
also the parametricity theorem. Yeah.
Yeah.
Yeah. So you need the parametricity theorem to hold. And yeah, the fact that you've done it polymorphically. But that's the point. Like you've designed your language so that you get the parametricity theorem. And that's good programming language design. I think
Yeah.
that's the whole point. It's like when we define this using a simple, elegant, and um, expressive mathematical system, for example, some functional language, so system F in this case,
Mm.
then you get these elegant theorems on top of it, which allow us to reason about programs without having to look at incredibly difficult things to look at. For example, the specific implementation of that program.
Mm. Mm-hmm.
Yeah. So it's really cool, but I don't fully understand it.